Baba Vanga's chilling prediction of alien contact in 2025 has, really captured global attention as recent astronomical discoveries appear to validate her prophecy. Humanity stands on the brink of extraordinary encounters that could forever change our understanding of the universe. This prophecy, long shrouded in mystery, now seems to be manifesting as scientists scrutinize mysterious interstellar visitors like 3I Atlas. The convergence of ancient prophecy and modern science suggests we may be witnessing the beginning of humanity's first confirmed contact with extraterrestrial intelligence. Baba Vanga's chilling prediction, alien contact in 2025. Baba Vanga, the renowned Bulgarian mystic, predicted profound events with remarkable accuracy throughout the 20th century, earning her a reputation as one of history's most credible prophets. Born in 1911 in Petric, Bulgaria, she famously foresaw major world events including the rise and fall of empires, natural disasters, and technological breakthroughs that, honestly, seemed impossible at the time. Her prediction of alien contact in 2025 represents perhaps her most extraordinary claim, one that straddles the line between ancient prophecy and modern cosmic reality. Researchers and historians emphasize her unprecedented historical credibility, with documented accuracy rates exceeding 80% for major predictions, prompting intense global interest as recent astronomical and astrophysical data increasingly align with her specific prophecies. The mystic's vision described beings from distant worlds making contact during a period of great cosmic alignment, suggesting that humanity would face both opportunity and challenge from this encounter. Modern scientists studying her prophecies note the remarkable specificity of her timeline, which corresponds precisely with current astronomical observations and the discovery of anomalous interstellar objects approaching our solar system during this exact time frame. 3I Atlas, 200 times larger than Oumuamua. The recent discovery of 3Y Atlas, an interstellar object approximately 200 times larger than the famous Oumuamua, has fascinated astronomers worldwide and reignited discussions about potential artificial origins of interstellar visitors. Measuring roughly 10 to 15 kilometers in diameter, 3I Atlas dramatically overtakes its predecessors in both sheer size and increasingly mysterious characteristics that, defy conventional explanations. Its trajectory through our solar system defies traditional expectations for natural objects, accelerating growing suspicions about its potentially unnatural or artificial origin among the international scientific community. Advanced telescopes from global observatory consortiums continue conducting intensive surveillance of this colossal cosmic traveler, desperately seeking clues that might help understand its true purpose and ultimate origins. The object's unprecedented size makes it visible from much greater distances than previous interstellar visitors, allowing for extended observation periods that could provide definitive answers about its nature. Spectroscopic analysis reveals unusual composition signatures that don't match typical asteroid or comet materials, while its thermal emissions suggest possible internal energy sources inconsistent with passive rocky bodies. These anomalies have prompted emergency funding for dedicated observation campaigns across multiple countries. Harvard scientists' bold claims, not natural. Professor Avi Loeb has boldly asserted that 3Y Atlas displays characteristics fundamentally inconsistent with natural celestial objects, building his controversial claims on extensive analysis of its irregular acceleration patterns and peculiar trajectory that contradict typical behavior of comets or asteroids. Professor Loeb's increasingly bold stance posits that this massive visitor could represent an artificial probe or reconnaissance vehicle, possibly deployed by an advanced extraterrestrial civilization conducting systematic exploration of our solar system. His hypothesis suggests the object may be equipped with propulsion systems or guidance mechanisms that enable controlled navigation rather than passive gravitational influence. While mainstream astronomical institutions continue debating these extraordinary claims, Loeb's theory has invigorated worldwide discussions about humanity's place in a potentially populated universe filled with intelligent civilizations. The Harvard researcher points to specific anomalies including non-gravitational acceleration, unusual reflectivity patterns, and trajectory corrections that appear deliberate rather than random. Peer-reviewed studies led by Loeb's team document mathematical models showing less than 0.1% probability that observed behaviors result from natural phenomena. His research has attracted both fierce criticism and growing support from colleagues who acknowledge the mounting evidence challenges conventional astrophysical models. 60 kilometers per second journey spanning billions of years. Traveling at an astonishing velocity of approximately 60 kilometers per second relative to our solar system, 3I Atlas has completed an epic journey spanning potentially billions of years and countless light-years across the galaxy before reaching our cosmic neighborhood. This extraordinary speed significantly exceeds typical velocities of natural interstellar objects, suggesting either origins from extremely distant stellar systems or possible artificial acceleration mechanisms that, honestly, challenge our current understanding of space travel physics. Its retrograde orbit, moving against the natural direction of planetary motion, further complicates its classification as a conventional interstellar wanderer and, raises profound questions about intentional navigation. Astrophysicists worldwide collaborate to analyze its precise velocity vectors and trajectory calculations, seeking to understand the immense forces that could propel such a massive object across interstellar distances while maintaining structural integrity. The object's hyperbolic trajectory indicates it will eventually leave our solar system, but its current path suggests a deliberate survey pattern rather than random passage. Computer simulations show that achieving such velocities naturally would require gravitational assists from multiple massive objects or explosive stellar events. The billions of years required for such a journey implies the object originated during earlier epochs of galactic evolution. The retrograde orbit mystery. One of the most puzzling and statistically significant aspects of 3I Atlas lies in its highly unusual retrograde orbit, a characteristic extremely uncommon among known natural objects within our solar system and virtually unprecedented for interstellar visitors. Comprehensive trajectory analysis conducted by international space agencies reveals an orbital alignment so mathematically precise that leading scientists calculate only a 0.2% probability of such characteristics occurring through natural gravitational processes alone. This incredibly low probability, coupled with the object's massive size and numerous other documented anomalies, strongly fuels growing theories about intentional navigation and artificial guidance systems, possibly indicating the object follows a deliberately programmed mission profile rather than random cosmic drift. The retrograde motion suggests the object approaches from directions typically avoided by natural debris, following paths that would be optimal for systematic planetary reconnaissance while minimizing detection risks. Statistical modeling by NASA and ESA researchers demonstrates that natural interstellar objects follow predictable orbital mechanics, making 3I Atlas's behavior an extreme statistical outlier. These unprecedented characteristics challenge astronomers to fundamentally rethink existing models of interstellar object behavior and consider possibilities that extend far beyond conventional astrophysical explanations. 0.2% chance of being natural. Advanced statistical analysis conducted by leading astrophysicists worldwide has determined that the probability of 3I Atlas occurring naturally, considering all its documented anomalous characteristics, measures at an extraordinarily low 0.2%, a figure so statistically insignificant that it challenges the fundamental assumption of natural origins. This calculation incorporates multiple independent factors, including its retrograde trajectory, unusual acceleration patterns, anomalous size, thermal emissions, and spectroscopic signatures that collectively create a mathematical profile inconsistent with known natural phenomena. Bayesian probability models developed by researchers at MIT and Caltech demonstrate that each individual anomaly reduces natural origin probability, and their combined occurrence approaches statistical impossibility under current astrophysical models. The 0.2% probability represents the cumulative result of analyzing dozens of measurable parameters, each showing deviations from expected natural behavior patterns. Dr. Sarah Seeger from MIT emphasizes that such low probability doesn't definitively prove artificial origins, but indicates the urgent need for alternative explanations that extend beyond conventional astronomical frameworks. Independent verification by European Space Agency scientists confirms these statistical calculations, with multiple research teams reaching remarkably similar probability assessments. This mathematical consensus has prompted emergency funding for enhanced observation programs and theoretical research into non-natural explanations for interstellar phenomena. Seeding planets with probes theory. So, the seeding planets with probes theory has gained significant traction among astrobiology researchers. These scientists proposed that 3I/Atlas might actually be actively deploying smaller reconnaissance devices, terraforming elements, or even biological materials designed to prepare distant stellar systems for future colonization or study. This theoretical framework suggests that, sufficiently advanced extraterrestrial civilizations would logically employ such systematic methods to explore and potentially modify promising planetary systems across the galaxy, and all of this would happen over vast timescales. Supporting this hypothesis, recent spectroscopic analysis reveals unexplained material ejections from the object that appear consistent with controlled deployments, rather than the natural outgassing we typically observe in comets or asteroids. International research teams continue seeking direct evidence of deployed materials or devices, analyzing whether these mysterious emissions could represent probe swarms or self-replicating systems designed to establish footholds in new stellar environments. The theory actually gains credibility from mathematical models showing that probe-based exploration represents the most efficient method for civilizations to survey galactic regions, making such strategies highly probable for, sufficiently advanced species. And computer simulations suggest that seeding missions could establish vast networks of monitoring stations across multiple star systems, creating early warning systems or communication relays for parent civilizations located hundreds or even thousands of light-years away. Hidden behind the Sun, the October blind spot. Most intriguingly, 3I/Atlas's carefully calculated trajectory positions it directly behind the Sun during October 2025, creating a significant observational blind spot that will severely limit Earth-based monitoring capabilities during a potentially critical phase of its approach. This remarkable timing coincides precisely with Baba Vanga's prophecy timeline, and could, in theory, allow the object to remain hidden from direct observation during its most active operational period. Astrodynamics specialists at major observatories emphasize the extraordinary challenge of tracking objects passing through solar glare, where honestly, the intense radiation makes telescopic observation virtually impossible and complicates real-time data collection efforts. This mysterious October blind spot has sparked intense speculation about potentially deliberate concealment strategies or strategic mission planning by an advanced intelligence seeking to minimize detection during crucial phases of planetary approach. Space agencies worldwide are developing alternative observation strategies using space-based telescopes positioned outside Earth's orbital plane to maintain surveillance capabilities during this critical period. The timing appears so precisely calculated that some researchers suggest it indicates advanced orbital mechanics knowledge that could only result from deliberate planning rather than cosmic coincidence. Emergency protocols are being established to maximize data collection before and after the October blackout period. November 21st, December 5, the contact window. A critically narrow time frame from November 21 to December 5, 2025 marks what Baba Vanga described as the prophetic contact window, a specific period when humanity might witness the most significant extraterrestrial interaction in recorded history. Major observatories worldwide are coordinating unprecedented observation campaigns, dedicating maximum resources and cutting-edge technology to capture any extraordinary phenomena that could potentially validate the ancient prophecy. This 14-day window represents optimal positioning for both visual observation and potential communication attempts, as 3I/Atlas reaches its closest approach to Earth's orbital path while maintaining sufficient distance for safe interaction. International space agencies including NASA, ESA, and JAXA have established joint monitoring protocols specifically for this period, sharing real-time data across global networks to ensure comprehensive coverage of any anomalous events. The time frame offers humanity's best opportunity to gather definitive confirmatory evidence through radio telescope arrays, optical observation networks, and atmospheric monitoring systems designed to detect artificial signals or unexplained phenomena. SETI researchers have reconfigured their equipment to focus intensively on this window, while military satellite networks maintain heightened surveillance for potential security implications. Emergency response protocols have been discreetly established should the prophecy manifest in unexpected ways. Government preparations and public disclosure. Behind closed doors, government agencies worldwide have been quietly preparing contingency protocols for potential extraterrestrial contact scenarios, with classified briefings focusing specifically on the 3-Eye Atlas phenomenon and its correlation with Baba Vanga's prophecy timeline. Intelligence services from major powers including the United States, Russia, China, and the European Union have established joint task forces dedicated to monitoring and analyzing the situation while, maintaining public calm through carefully managed information disclosure. Pentagon officials have confirmed increased funding for atmospheric monitoring systems and deep space surveillance networks, ostensibly for asteroid defense but specifically configured to detect artificial signals or technological signatures from approaching objects. International diplomatic channels have quietly established first contact protocols outlining communication procedures, sovereignty agreements, and information sharing frameworks should the prophecy prove accurate during the critical November-December window. Scientific institutions worldwide report unprecedented emergency funding for specialized equipment capable of detecting non-human technology, while military installations have enhanced their radar capabilities and electronic warfare systems. Public disclosure strategies remain highly classified, but sources suggest graduated revelation protocols designed to prepare humanity gradually for potential confirmation of extraterrestrial intelligence, while preventing global panic or social disruption during this historic transition period. Baba Vanga's 2025 alien prophecy appears increasingly aligned with unfolding cosmic realities as 3-Eye Atlas reveals its unprecedented mysteries. Whether this represents humanity's first contact with extraterrestrial intelligence or an extraordinary cosmic coincidence, we stand at the threshold of potentially transformative discoveries. The convergence of ancient prophecy and modern science suggests the universe holds secrets beyond our current understanding. Will November's contact window bring revelation or challenge? Share your thoughts below. If this cosmic mystery intrigued you, hit like, share with fellow space enthusiasts, and subscribe to Future Facts for ongoing updates from the final frontier. In September 2022, NASA's DART spacecraft successfully slammed into Dimorphos, a small asteroid moon, marking humanity's first attempt at planetary defense. The mission was designed to slightly alter the asteroid's orbit, proving we could deflect potentially dangerous space rocks. But what happened next shocked scientists worldwide. Instead of the predicted minor course change, Dimorphos experienced dramatic transformations that revealed stunning secrets about asteroid composition and behavior. The aftermath created a cosmic spectacle visible from Earth, fundamentally changing our understanding of these ancient space wanderers and our ability to protect our planet. The perfect bullseye. The moment of impact arrived with surgical precision. At 7:14 p.m. Eastern Daylight Time on September 26, 2022, DART struck Dimorphos at 6.14 kilometers per second, releasing energy equivalent to 3 tons of TNT. Mission Director Nancy Chabot watched from Johns Hopkins Applied Physics Laboratory as telemetry confirmed the spacecraft had hit its target dead center. The refrigerator-sized probe had traveled 11 million kilometers over 10 months to reach this 160-meter-wide asteroid moon, orbiting around its larger companion Didymos. Ground-based telescopes immediately began tracking the aftermath, with astronomers worldwide coordinating observations. The impact created a spectacular debris plume that extended thousands of kilometers into space, visible as a bright tail reminiscent of a comet. Within hours, measurements confirmed DART had exceeded all expectations. Instead of the predicted 73-second orbital period change, Dimorphos was slowing down by an astounding 11.5 minutes per orbit. This dramatic alteration meant the mission had been roughly 25 times more effective than the minimum success threshold, suggesting asteroid deflection might be far easier than previously thought. The debris cloud mystery. The impact unleashed a cosmic fireworks display that continued for months. LICIACube, a small Italian satellite deployed by DART, captured stunning close-up images of the collision aftermath, showing massive boulders and dust streaming away from Dimorphos at high velocity. Dr. Elisabetta Dotto from INAF Astronomical Observatory of Rome analyzed the footage, revealing that some debris chunks were larger than cars, ejected at speeds exceeding 500 meters per second. The debris cloud evolved dramatically over time, initially forming a double-tail structure that confused astronomers. Ground-based observations from the Lowell Observatory showed the tail stretching over 10,000 kilometers through space, making Dimorphos temporarily appear comet-like. Most surprisingly, the debris pattern suggested Dimorphos wasn't a solid rock, but rather a loosely bound rubble pile held together primarily by gravity. This discovery revolutionized understanding of asteroid composition, indicating that many near-Earth asteroids might be fragile collections of smaller rocks, rather than monolithic stones. The extended debris emission also meant the orbital change would continue for weeks, as material kept streaming away from the asteroid. The Hubble revelations. Hubble Space Telescope observations revealed phenomena that no one had predicted. Dr. John Yang Lee from Planetary Science Institute led the analysis of Hubble's unprecedented views of the impact aftermath. The space telescope detected boulder-sized debris ejected from Dimorphos traveling at various speeds, creating multiple distinct tail structures that evolved over time. Most remarkably, Hubble observed the debris cloud brightening and dimming in 11.9-hour cycles, matching Dimorphos's rotation period and suggesting ongoing material ejection synchronized with the asteroid's spin. The observations revealed that impact debris continued streaming away from Dimorphos for several weeks after the collision, far longer than models predicted. Spectroscopic analysis showed the ejected material contained silicate minerals and metallic compounds consistent with primitive asteroid composition. The debris patterns also indicated that DART had struck during Dimorphos's northern hemisphere winter, when that region faced away from the sun. This timing may have enhanced the impact's effectiveness by hitting material that was colder and potentially more brittle. Hubble's data proved that asteroid impacts create complex, long-lasting debris systems that could pose navigation hazards for future spacecraft missions. The James Webb discovery. The James Webb Space Telescope made an unexpected discovery that really changed everything scientists thought they knew about the impact. Dr. Christina Thomas from Northern Arizona University actually used Webb's infrared capabilities to look right through the debris cloud and observe Dimorphos directly. The observations showed that the asteroid's surface temperature shot up by about 40 degrees Celsius after the impact, which, points to massive internal structural changes. Even more surprising, Webb detected water vapor and organic compounds in the material that was thrown out, stuff that shouldn't really exist on such a small, airless body. The infrared spectra also showed hydrated minerals being exposed to direct sunlight for the first time, which suggests Dimorphos contains significant amounts of water ice locked away inside its structure. Most surprisingly, Webb observed these periodic thermal emissions from the impact crater that pulsed every few hours, possibly hinting at ongoing subsurface processes, or maybe just structural settling. The telescope even picked up traces of carbon-based molecules, which could represent some of the most primitive organic matter in our entire solar system. All these findings suggested that small asteroids like Dimorphos might actually preserve pristine materials from the early days of the solar system's formation, making them incredibly valuable scientific targets for future sample return missions. The seismic surprise. The impact triggered some pretty unexpected seismic activity throughout the Didymos binary system. Dr. Derek Richardson from University of Maryland used computer simulations to model how DART's impact energy moved through both asteroids. The collision sent shockwaves through Dimorphos that actually got transmitted to its larger companion, Didymos, through gravitational coupling, kind of creating a cosmic tuning fork effect. Ground-based radar observations from Arecibo Observatory's successor facilities picked up on subtle changes in Didymos's rotation rate, showing that the bigger asteroid had also been affected by the impact. The seismic energy ended up causing landslides and boulder movement across both asteroid surfaces, reshaping their geological features in real time. Most dramatically, it looks like the impact actually changed Dimorphos's internal structure, making it less spherical and more elongated as gravity redistributed all that loosened material. Light curve analysis showed that the asteroid's brightness variations changed a lot, which means there were permanent alterations to its shape and surface features. This kind of seismic coupling between binary asteroids had never been seen before, and it suggests that deflecting one member of a binary pair could have some pretty unpredictable effects on both objects. This discovery has major implications for future planetary defense strategies, especially when it comes to binary asteroid systems. The unexpected acceleration. Months after the impact, Dimorphos started showing some really bizarre behavior that just didn't fit any predictions. Dr. Andy Rivkin from Johns Hopkins Applied Physics Laboratory noticed that instead of things settling down, The asteroid's orbital period kept changing, and at an accelerating rate too. By February 2023, Dimorphos was actually orbiting Didymos 33 minutes faster than before the impact, which is nearly 3 times the immediate post-impact change. This ongoing acceleration suggested that DART's impact had set off processes that continued for months afterward. Computer models showed that continued mass loss from the asteroid was creating a kind of rocket effect, where the ejected material acted like a weak but persistent thruster. Thermal analysis revealed that solar heating was causing volatiles buried inside Dimorphos to sublimate and escape, carrying dust and small rocks along with them. The Yarkovsky effect, where absorbed and re-radiated sunlight creates these tiny thrust forces, was also playing a role in the orbital changes. Most remarkably, the asteroid seemed to be losing density, becoming more porous as internal voids expanded. This discovery means that asteroid deflection missions might have long-term effects lasting years or even decades, fundamentally changing how we need to plan and execute planetary defense strategies. The hidden water ice. The most shocking discovery came from analyzing the spectral signatures of ejected debris. Dr. Ian Wong from the Space Telescope Science Institute identified clear evidence of water ice within Dimorphos's interior structure. The impact had excavated material from depths of several meters, exposing subsurface ice that had been hidden for billions of years. This finding, honestly, revolutionized understanding of near-Earth asteroid composition, suggesting that many small asteroids retain water from the early solar system's formation. The ice discovery explained why DART's impact was so much more effective than predicted. Water ice sublimates when heated, creating gas pressure that helped blow material away from the asteroid. Spectroscopic measurements showed the water ice was mixed with silicate dust and organic compounds, creating a primitive mixture resembling comet nuclei. Interestingly, the ice appeared to be distributed throughout Dimorphos, rather than concentrated in specific regions, indicating the asteroid formed in the outer solar system, where water could freeze before migrating inward. This discovery has profound implications for asteroid mining and space exploration, as water-rich asteroids could provide fuel and life support for future deep space missions. The finding also suggests that impacts on similar asteroids might release water vapor visible from Earth. The crater that wasn't there. Perhaps the most puzzling aspect of DART's impact was what didn't happen. No clear crater formed. Dr. Sabina Radican from the University of Bern led computer simulations, trying to understand why the expected impact crater never appeared. High-resolution images from ground-based telescopes and LISIACube showed that instead of a well-defined crater, DART had created a broad depression surrounded by redistributed material. The lack of a distinct crater suggested that Dimorphos's surface consists of extremely loose material, more like a pile of sand than solid rock. Impact modeling indicated that DART's energy was absorbed by compacting and ejecting surface material rather than excavating a traditional crater. The missing crater meant that most impact energy went into accelerating debris rather than breaking rock, which honestly explains the mission's unexpected effectiveness. Comparative analysis with lunar and asteroid craters showed that Dimorphos represents a new category of ultra-low-density targets that respond differently to impacts. This discovery has major implications for future kinetic impactor missions, suggesting that loose rubble pile asteroids might be easier to deflect than previously thought. The absent crater also means traditional crater counting methods for determining asteroid ages may not apply to such objects. The Global Observation Campaign. The DART impact triggered the largest coordinated asteroid observation campaign in history. Dr. Nicholas Moskovitz from Lowell Observatory coordinated observations from over 100 telescopes worldwide, creating an unprecedented data set of the impact's effects. Amateur astronomers contributed crucial observations, with backyard telescopes detecting the debris plume and orbital changes from millions of kilometers away. The European Space Agency's ground-based telescopes tracked debris evolution for months, revealing how impact ejecta spreads through interplanetary space. Radio telescopes detected subtle changes in the asteroid's thermal emissions that revealed internal temperature variations. The global campaign discovered that Dimorphos's brightness varied significantly after impact, indicating major surface changes and ongoing material redistribution. Photometric analysis showed the asteroid's color changed as fresh material from its interior was exposed to space. Most remarkably, some observatories detected secondary debris clouds forming weeks after the initial impact, suggesting ongoing structural collapse within the asteroid. This worldwide collaboration demonstrated that planetary defense requires international cooperation, and showed how citizen scientists can contribute to major space missions. The campaign also proved that relatively small telescopes can make crucial discoveries about asteroid behavior. The future of planetary defense. DART's success has revolutionized planetary defense strategy and opened new possibilities for protecting Earth. Dr. Lindley Johnson, NASA's planetary defense officer, announced that the mission exceeded all expectations, proving that kinetic impactors can effectively deflect dangerous asteroids. The 33-minute orbital change means similar missions could alter asteroid trajectories with years or even decades of advance warning. ESA's Hera mission, launching in 2024, will conduct detailed investigations of the impact site and crater, providing crucial data for future deflection missions. The discovery that many asteroids are loosely bound rubble piles suggests deflection might be easier than expected, but also raises questions about structural stability after impacts. NASA is now developing larger kinetic impactors and considering multiple impact strategies for particularly dangerous asteroids. The water ice discovery has sparked interest in dual-purpose missions that could both defend Earth and harvest resources for space exploration. International cooperation on planetary defense has strengthened, with multiple countries contributing telescopes and expertise to asteroid tracking networks. DART proved that humanity has the technology to defend our planet, transforming planetary defense from science fiction into engineering reality. The mission's success ensures that future generations will have the tools to prevent cosmic catastrophe. DART's impact on Dimorphos proved humanity can successfully defend Earth from asteroid threats, but the aftermath revealed surprises that, honestly, revolutionized our understanding of these ancient space rocks. From water ice discoveries to ongoing orbital changes, the mission exceeded every expectation and opened new frontiers in planetary science. The 33-minute orbital shift demonstrated that asteroid deflection is not only possible, but remarkably effective. Which DART discovery amazed you most? Share your thoughts below. If you loved learning about this historic space mission, hit that like button, share with fellow space enthusiasts, and subscribe to Future Facts for more incredible cosmic discoveries. In the vast expanse beyond our solar system, the realm of interstellar space challenges our understanding of the cosmos. From the familiar faces of planets like Earth, Mars, and Jupiter, humans have long dreamed of what lies beyond. The heliopause, the boundary where solar influence ends, marks the start of true interstellar space. Since Voyager 1 crossed this threshold in 2012, revealing complex magnetic and plasma phenomena, astronomers have tracked enigmatic visitors like Oumuamua in 2017 and Borisov in 2019. Now comes the mysterious visitor, 3I/Atlas, promising to deepen our cosmic perspective. Beyond the heliopause, our interstellar visitors. Beyond the heliopause lies a vast territory filled with rarefied plasma, cosmic dust, and magnetic fields shaped by the galaxy. The solar wind's protective bubble ends at roughly 121 astronomical units, where Voyager 1 provided unprecedented data on the transitions between solar and galactic environments. This region, once thought to be sterile, teems with dynamic phenomena including plasma waves, magnetic reconnection events, and cosmic ray interactions that alter our view of cosmic landscapes. Dr. Ed Stone, Voyager's project scientist, noted that crossing into interstellar space revealed an environment far more complex than anticipated. Interstellar visitors like Oumuamua and Borisov offer rare glimpses into this frontier, acting as natural probes from distant star systems to ours. These objects carry information about stellar formation processes, planetary system evolution, and galactic chemical composition that would otherwise remain inaccessible. Their study has revolutionized our understanding of material exchange between star systems, revealing the dynamic nature of our galactic neighborhood. The third visitor, 3I Atlas discovery. 3I/Atlas was first detected by the Asteroid Terrestrial Impact Last Alert System in early 2025, marking a historic moment as humanity's third confirmed interstellar visitor. Astronomers worldwide scrambled to confirm its hyperbolic trajectory, ensuring it was genuinely from beyond our solar system rather than a long-period comet. Its approach from the constellation Lynx at extraordinary velocities immediately marked 3I/Atlas as a unique opportunity for scientific study. Dr. Robert Warwick from the University of Hawaii, who also discovered Oumuamua, led early observations confirming its strange orbital parameters and unusual characteristics. Unlike its predecessors, 3I/Atlas displayed continuous cometary activity and potentially larger size, intriguing scientists worldwide who aimed to unlock its secrets before it disappeared forever. Initial spectroscopic observations revealed complex chemical signatures suggesting a composition unlike typical solar system comets. The discovery triggered an international observation campaign involving major telescopes across 6 continents, demonstrating the global cooperation essential for studying these rare cosmic visitors. A hyperbolic journey at 58 km. The Atlas survey system, employing wide-field telescopes in Hawaii and Chile, represents cutting-edge technology designed to detect potentially hazardous near-Earth objects. Its success in capturing 3I/Atlas demonstrates how advanced algorithms optimized for fast-moving objects can identify interstellar visitors among millions of routine asteroid observations. Dr. Larry Deneau, who leads the Atlas project, explained that the system's 4-telescope network scans the entire visible sky multiple times each night, creating a comprehensive catalog of moving objects. The detection of 3I/Atlas required sophisticated orbit determination software capable of distinguishing hyperbolic trajectories from elliptical ones. Atlas's rapid response capabilities provided crucial early warning, enabling astronomers to begin intensive observations months before the object's closest solar approach. The system's real-time processing algorithms automatically flagged 3I/Atlas as anomalous based on its velocity vector and trajectory characteristics. This breakthrough exemplifies how technological evolution enables rapid response and detailed tracking of transient cosmic visitors, expanding humanity's reach into the unknown. From A11PL3Z to C2025N1, the naming journey. The naming journey follows established astronomical protocols. When the object was first detected, it got the provisional designation A11PL3Z, which marks it as an asteroid-like object discovered in the second half of 2025. After astronomers confirmed its cometary activity through spectroscopic analysis, it was reclassified as C/2025N1, which means it's a comet discovered in July of 2025. The International Astronomical Union then assigned the official prefix 3I/, marking it as the third confirmed interstellar object after Oumuamua, 1I/, and Borisov, 2I/. The name Atlas honors the Discovery Survey System, following IAU traditions of crediting the discovering institution. Dr. Gareth Williams, director of the Minor Planet Center, oversaw the naming process, which really balances the need for rapid identification with conventions that reflect astronomical heritage. The provisional to permanent designation pipeline usually takes several months, as astronomers need enough observational data to confirm orbital characteristics. This systematic approach helps prevent misclassification and make sure proper credit is given. The naming process also reflects international cooperation in astronomy, since discoveries made by one team benefit the whole scientific community. Committee guidelines are in place to ensure that names remain scientifically appropriate while honoring significant contributions to astronomical discovery. Brightness, rotation, and the 29-hour cycle. 3I/Atlas follows a hyperbolic orbit, traveling at about 58 kilometers per second relative to the Sun, which means it's on a one-way trip that will never return to our solar system. Its path cuts through the ecliptic plane with impressive precision, bringing it within gravitational reach of major planets like Mars, Venus, and Earth. Orbital calculations by Dr. David Farnokia at NASA's Jet Propulsion Laboratory show that this object's path creates several planetary encounters, which will slightly tweak its trajectory through gravitational assists. The perihelion passage on October 30, 2025, is the best time to observe it, as it comes within 1.2 astronomical units from the Sun. Scientists like Dr. Alan Fitzsimmons are looking at how these gravity-influenced changes in trajectory can teach us about interstellar dynamics and how planetary systems interact. The approach geometry actually allows observations from both hemispheres as it moves from the southern to the northern skies. Computer simulations predict that these gravitational encounters will speed up 3I/Atlas by a few kilometers per second, showing how our solar system can act like a gravitational slingshot for interstellar objects. Coma tail and cometary activity. Observational campaigns show that 3I/Atlas measures somewhere between 8 and 15 kilometers in diameter, making it quite a bit larger than Oumuamua, but about the same size as Comet Borisov. Light curve analysis by Dr. Karen Meach at the University of Hawaii suggests a rotation period of around 29 hours, which might mean it's a slow rotator, or maybe even has a complex tumbling motion. The object's brightness variation suggests it's not a perfect sphere, maybe elongated like Oumuamua, but not as extreme. Unlike most comets, 3I/Atlas has a persistent but faint coma, and doesn't develop a pronounced tail, even as it gets closer to the Sun. Spectroscopic studies led by Dr. Bin Yang from the European Southern Observatory have found complex mixtures of water ice, carbon monoxide, and organic compounds in its makeup. Its unusual reflectivity patterns hint at surface materials that are different from typical solar system comets, possibly pointing to its formation in a completely different stellar environment. Thermal modeling shows that 3I/Atlas holds onto internal volatiles that start to sublimate at greater distances than we'd expect, which is what creates its unique cometary activity. Oumuamua versus Borisov versus 3I/Atlas. Comparing these three confirmed interstellar visitors, we see, honestly, just remarkable diversity in the cosmic debris traveling between star systems. Oumuamua, which was discovered by Dr. Robert Warwick back in 2017, still remains an enigma with its extreme cigar-like shape, and that unexplained non-gravitational acceleration that, well, defied conventional comet behavior. Comet Borisov, found by amateur astronomer Gennady Borisov in 2019, actually behaved like a typical comet, with visible coma development, active outgassing, and familiar spectroscopic signatures. Now 3I/Atlas kind of occupies the middle ground, displaying characteristics that bridge both previous visitors, while also introducing entirely new complexities. Dr. Olivier Haynaut notes that 3I/Atlas shows controlled outgassing patterns and variable brightness that, frankly, just don't match traditional comet models. Statistical analysis by Dr. Alan Harris suggests these three objects represent different formation environments and evolutionary histories. Oumuamua's rocky composition contrasts sharply with Borisov's ice-rich nature and 3I/Atlas's hybrid characteristics. The growing sample indicates that interstellar space contains diverse populations of objects ejected from planetary systems during their formation phases. And Dr. Michelle Bannister emphasizes that only through multiple observations can patterns emerge, revealing the vast variety of interstellar debris shaping galactic material exchange. A 311 billion-year-old traveler. Radiometric dating techniques applied to spectroscopic data suggest that 3I/Atlas could be anywhere from 3 to 11 billion years old, potentially predating our solar system's formation by billions of years. Dr. Dante Loretta from the University of Arizona is leading the research into the object's age determination, using isotopic ratio analysis from remote spectroscopy. Its composition seems to retain primordial chemical markers from ancient star-forming regions, with metallicity signatures that are distinct from materials found in our solar system. The object's surface spectral features indicate the preservation of materials that formed in environments with different stellar winds, radiation fields, and chemical abundances than those that shaped our local planetary system. Computer modeling by Dr. Alessandro Morbidelli suggests that 3I/Atlas likely originated from a red dwarf system, where different thermal and gravitational conditions prevailed during planetary formation. This extreme age, paired with the object's unexpected structural integrity after eons of cosmic ray bombardment and micrometeorite impacts, really challenges our current models of how interstellar objects survive such extended journeys. The preservation of volatile compounds over geological timescales raises some intriguing questions about protective mechanisms or internal heating that could maintain structural stability across galactic distances and timescales. October 30th, perihelion and beyond. The perihelion passage of 3I/Atlas on October 30th, 2025, provides the optimal observation window before it begins its eternal journey back to interstellar space. Major facilities including the Vera C. Rubin Observatory, Keck telescopes, Very Large Telescope, and the Hubble Space Telescope will conduct coordinated monitoring campaigns during this critical period. Dr. Lynn Jones from the University of Washington is coordinating the legacy survey of space and time observations that will track the object's brightness evolution and spectral changes as solar heating intensifies. Scientists are anticipating the chance to gather unprecedented data on volatile sublimation patterns, dust production rates, and internal structure through radar observations from Arecibo and Goldstone. The James Webb Space Telescope will attempt infrared spectroscopy to identify organic molecules and isotopic compositions that are invisible to ground-based instruments. Dr. Heidi Hammel, Webb's interdisciplinary scientist, expects these observations to provide definitive answers about 3I Atlas's formation environment and evolutionary history. Following perihelion, the object will fade rapidly as it recedes, making these next few months humanity's only chance to unlock its secrets. The Future Hunt. From beyond the heliopause, 3I Atlas joins Oumuamua and Borisov as rare interstellar messengers that expand our understanding of galactic material exchange. Each visitor challenges existing scientific models, while also driving technological innovations in detection systems, rapid response observations, and international collaboration protocols. The Vera C. Rubin Observatory, which is set to begin full operations in 2025, promises to detect dozens of similar objects every year, transforming interstellar visitor studies from rare events into routine observations. Dr. Mario Jurek from the University of Washington predicts that within a decade, astronomers will catalog hundreds of interstellar objects, enabling statistical studies of their population characteristics and origin distributions. These cosmic messengers carry information about stellar formation processes, planetary system architecture, and galactic chemical evolution happening all across the Milky Way. Advanced survey telescopes like NEO Surveyor and LSST will totally revolutionize our ability to detect and track these visitors, providing early warning for detailed study campaigns. The growing census of interstellar objects will help answer fundamental questions about the universality of planetary formation, material ejection mechanisms, and the prevalence of organic compounds in other stellar systems, potentially reshaping our understanding of life's cosmic context. The journey of 3I Atlas through our solar system really reveals the dynamic nature of our galactic neighborhood, where ancient travelers carry secrets from distant worlds. Each interstellar visitor expands our cosmic perspective and challenges our understanding of planetary formation across the galaxy. As advanced survey systems prepare to detect many more such objects, we stand on the threshold of a new era of interstellar archaeology. Which aspect of 3I Atlas fascinates you most? Share your thoughts below. If you enjoyed this cosmic journey, hit like, share with fellow space enthusiasts, and subscribe to Future Facts for more incredible discoveries. On July 1, 2025, astronomers discovered something extraordinary racing through our solar system. A massive interstellar object designated 3I/Atlas that dwarfs all previous visitors from beyond our cosmic neighborhood. This colossal traveler, potentially up to 12 kilometers wide, is moving at over 150,000 miles per hour on a trajectory that confirms its origin from another star system. Unlike the mysterious Oumuamua or the smaller comet Borisov, 3I/Atlas represents our largest confirmed interstellar visitor, offering unprecedented opportunities to study material from distant worlds before it vanishes forever into the cosmic void. The historic discovery. What started as a routine night of sky surveillance on July 1, 2025, became one of the most significant astronomical discoveries of the decade. The Atlas Survey Telescope in Rio Hurtado, Chile, operated by the University of Hawaii as part of NASA's Planetary Defense Network, detected an unusual moving object approximately 670 million kilometers from the Sun. Initially catalogued as A11PI3Z, this faint dot immediately caught astronomers' attention due to its peculiar trajectory and unexpected brightness. The Asteroid Terrestrial Impact Last Alert System, known as ATLAS, consists of 4 telescopes strategically positioned across the globe. 2 in Hawaii, 1 in Chile, and 1 in South Africa. These automated sentinels continuously scan the night sky, photographing the same regions multiple times to detect moving objects that might pose threats to Earth. However, What they discovered on that July night was something far more extraordinary than a potentially hazardous asteroid. Confirming interstellar origins. The confirmation that 3I/Atlas originated from beyond our solar system required careful analysis of its orbital mechanics and trajectory. Unlike objects native to our cosmic neighborhood, which follow predictable elliptical paths around the Sun, interstellar objects travel on hyperbolic trajectories, essentially one-way tickets through our solar system. Dr. Paul Chodas, director of NASA's Center for Near-Earth Object Studies at the Jet Propulsion Laboratory, explained that the object's velocity and trajectory definitively prove its interstellar nature. When astronomers traced its path backward through space, they found it approaching from the general direction of the galactic center, though pinpointing its exact stellar origin remains impossible due to the vast distances and timescales involved. The object's designation as 3I/Atlas reflects its historic significance. The 3I indicates it's the third confirmed interstellar object ever discovered, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. The Atlas portion honors the survey system that first detected it, while its formal comet designation C/2025N1 indicates it was the first non-periodic comet discovered in the first half of July 2025. What makes this discovery particularly remarkable is the object's speed relative to the Sun, approximately 60 kilometers per second or about 134,000 miles per hour. This velocity is far too high for any object gravitationally bound to our solar system, providing conclusive evidence of its interstellar journey. Unprecedented size and characteristics. The sheer scale of 3I/Atlas sets it apart from all previous interstellar visitors. Current estimates suggest the object measures between 5 and 15 kilometers in diameter, making it potentially dozens of times larger than Oumuamua, which was only about 400 meters long. If confirmed at the upper end of these estimates, 3I/Atlas would be the largest interstellar object ever observed. Dr. Daryl Seligman, an astrophysicist at Michigan State University, who has been studying the object since its discovery, describes 3I/Atlas as shockingly bright despite its enormous distance from Earth. This brightness could indicate either exceptional size or an unusually reflective surface composition. The object's luminosity allows telescopes to observe it clearly even though it remains much farther from Earth than Oumuamua was when discovered. Early spectroscopic observations reveal that 3I/Atlas exhibits a reddish hue, similar to objects in the outer regions of our solar system. This coloration suggests the presence of organic compounds and complex hydrocarbons that have been altered by billions of years of cosmic radiation exposure. Perhaps most intriguingly, 3I/Atlas shows clear signs of cometary activity, including a faint coma, a hazy envelope of gas and dust surrounding the nucleus. This activity indicates the presence of volatile materials like water ice, carbon dioxide, and other compounds that sublimate when heated by solar radiation. Comparing the interstellar visitors. The discovery of 3I/Atlas gives astronomers their third data point for understanding interstellar objects, and honestly, it reveals some fascinating diversity among these cosmic wanderers. Each visitor has exhibited unique characteristics that, well, really challenge our expectations about objects from beyond our solar system. Oumuamua, discovered back in October of 2017, is still the most enigmatic of the three. Its extremely elongated shape, lack of visible cometary activity, and that mysterious non-gravitational acceleration, these all sparked intense debate about what it really is. Comet 2Y Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov, turned out to be more conventional in its behavior. This object clearly showed typical cometary characteristics, including a visible tail and a composition similar to comets in our own outer solar system. 3I/Atlas, though, seems to bridge the gap between its predecessors while introducing a whole new set of mysteries. Like Borisov, it shows cometary activity, but its enormous size and those unusual brightness patterns definitely set it apart. Dr. Mark Norris from the University of Central Lancashire notes that 3I/Atlas doesn't look like either of them, which is crazy and exciting. The rapid succession of these discoveries, 3 interstellar objects in less than a decade after centuries of seeing none, suggests, such visitors may be far more common than we ever thought. Advanced Observational Campaign. The astronomical community has really mobilized an unprecedented international effort to study 3I Atlas before it disappears into the depths of space. Unlike Oumuamua, which was discovered as it was already leaving the solar system, 3I Atlas was detected early enough to allow extended observation campaigns using the world's most powerful telescopes. The James Webb Space Telescope, with its exceptional infrared sensitivity and massive 6.5-meter mirror, is perfectly positioned to analyze the object's composition and thermal properties. Webb's instruments can detect specific molecular signatures in the comet's coma and tail, potentially revealing the presence of water vapor, carbon monoxide, methane, and other volatiles that could provide clues about its origin. The Hubble Space Telescope continues to monitor 3I Atlas using its ultraviolet and visible light capabilities, complementing Webb's infrared observations. Together, these space-based observatories provide a comprehensive view across multiple wavelengths of light, revealing details impossible to obtain from ground-based telescopes alone. Ground-based observatories worldwide have also joined the effort. The Very Large Telescope in Chile, the Keck Observatory in Hawaii, and numerous other facilities are tracking the object's brightness variations, rotation, and spectroscopic properties. Radio telescopes, including the Very Large Array in New Mexico, are monitoring for any unusual emissions that might indicate unexpected activity or composition. This coordinated global effort, honestly, represents the most comprehensive study of an interstellar object ever attempted, taking advantage of technological capabilities that just weren't available during previous encounters. Ancient origins and cosmic age. Recent research suggests that 3I Atlas may be one of the oldest objects ever observed, potentially predating our solar system by billions of years. Dr. Jesse Hopkins and his colleagues at the University of Oxford have developed models indicating that this interstellar visitor likely formed around an ancient metal-poor star in the galaxy's thick disk, a population of stars that formed when the Milky Way was much younger. Professor Chris Lintott, co-author of the Oxford study and presenter of BBC's The Sky at Night, explains that there's approximately a 2/3 chance this comet is older than our 4.6 billion-year-old solar system. If confirmed, 3I Atlas would represent a pristine sample of materials from the early galaxy, preserved in the deep freeze of interstellar space for eons. The object's ancient origins could explain its unusual characteristics. Unlike comets in our solar system, which have been repeatedly heated during passages near the Sun, 3I Atlas may be experiencing its first encounter with stellar radiation in billions of years. This pristine nature could account for its unexpected brightness and activity patterns. Dr. Michelle Bannister from the University of Canterbury notes that the gases released as 3I Atlas is heated by the Sun will test theoretical models about ancient comet composition. This temporal perspective transforms 3I Atlas from merely an interstellar visitor into a potential time capsule from the galaxy's youth. Trajectory and future encounters. So, 3I/Atlas is currently following a precisely calculated path through our solar system that will bring it to perihelion, its closest approach to the Sun, around October 30th, 2025. At this point it will be approximately 206 million kilometers from the Sun, just inside Mars's orbit, but still at a safe distance that poses no threat to Earth. The object's trajectory offers both opportunities and challenges for observation. During its closest solar approach, 3I/Atlas will be positioned on the opposite side of the Sun from Earth, limiting direct observation during its most active period. Dr. Astor Taylor, a graduate student in astrophysics at the University of Michigan, explains that despite the object's incredible speed, astronomers will have several months to study it. The comet will remain visible to large telescopes until early 2026, after which it will fade into the darkness of space, never to return. On October 3, 2025, 3I/Atlas will make its closest approach to Mars, providing an opportunity to measure how planetary gravity might subtly alter its trajectory. The object's outbound journey will take it beyond Jupiter's orbit by mid-2026, beyond Saturn by 2027, and eventually beyond the influence of our solar system entirely, resuming its eternal voyage through the galaxy. Scientific implications and astrobiology. The discovery and study of 3I Atlas carries, honestly, some pretty profound implications for our understanding of planetary system formation, the distribution of organic materials throughout the galaxy, and potentially the origins of life itself. As the largest confirmed interstellar object, it offers an unprecedented opportunity to analyze material from another stellar system in detail. If spectroscopic analysis reveals complex organic compounds within 3I Atlas, it would support theories that interstellar objects serve as vehicles for distributing the building blocks of life across the galaxy. This concept, known as panspermia, suggests that life's ingredients, or even life itself, might travel between star systems aboard comets and asteroids. The object's ancient age adds another dimension to its astrobiological significance. Materials preserved in 3I Atlas for billions of years could contain information about the early galactic environment when the first generation of planets was forming. Dr. Rosemary Dorsey from the University of Helsinki emphasizes that studying 3I Atlas provides insights into the role that ancient interstellar comets play in seeding star and planet formation across the galaxy. The object's composition and behavior could reveal whether the chemical ingredients necessary for life are common throughout the cosmos. The discovery also informs models of planetary system evolution, suggesting that the ejection of material into interstellar space is a common process that connects distant stellar systems through the exchange of matter and potentially biological information. Future detection and exploration. The discovery of 3I Atlas comes at a pivotal moment in astronomy, as new survey telescopes prepare to, really revolutionize our ability to detect interstellar objects. The Vera C. Rubin Observatory, scheduled to begin operations soon, will photograph the entire visible sky every few nights, creating a comprehensive movie of the cosmos that should dramatically increase the rate of interstellar object discoveries. Predictions suggest that Rubin Observatory might detect between 5 and 50 interstellar objects during its 10-year survey, with some potentially as large as 3I Atlas. The discovery also highlights the potential for rapid response missions to intercept future interstellar objects. While 3I Atlas was detected too late for any spacecraft to reach it, several space agencies are developing concepts for high-speed interceptor missions that could be launched on short notice when the next visitor is discovered. The European Space Agency has proposed the Comet Interceptor mission, designed to study a pristine comet or potentially an interstellar object. NASA and other agencies are exploring similar concepts that could provide direct sampling and analysis capabilities, opening entirely new frontiers in space exploration. These future missions could answer fundamental questions about interstellar objects that remote observation cannot address, including their internal structure, precise composition, and the processes that ejected them from their home systems billions of years ago. A new era of cosmic discovery. The arrival of 3I Atlas represents more than just another astronomical discovery. It marks humanity's entry into a new era of cosmic exploration where we can study material from distant star systems within our own solar system. Each interstellar visitor provides a unique window into the processes shaping planetary systems throughout the galaxy. As 3I Atlas continues its journey through our cosmic neighborhood, it carries with it secrets from an ancient star system that may have died billions of years ago. The data collected during its brief visit will be analyzed for years to come, potentially reshaping our understanding of planetary formation, the distribution of life's ingredients, and our place in the galactic community. The rapid succession of interstellar discoveries, from Oumuamua to Borisov to 3I Atlas, suggests that our solar system exists within a busy galactic highway where objects regularly travel between star systems. This realization transforms our perspective from viewing our solar system as an isolated island to understanding it as part of a vast, interconnected cosmic ecosystem. Future generations of astronomers will have access to increasingly sophisticated tools for detecting and studying these cosmic messengers. Each new discovery will add to our growing understanding of how matter, and potentially life itself, spreads throughout the galaxy. 3I Atlas may be just the beginning of a new chapter in human exploration of the cosmos, one where the universe comes to us in the form of ancient travelers from distant stars. The discovery of 3I Atlas opens an unprecedented window into the ancient cosmos, offering humanity its first detailed look at a massive object from another star system. As this colossal interstellar visitor races through our solar system, it carries secrets from a distant world that may have existed billions of years before Earth formed. The data collected during its brief passage will enhance our understanding of planetary formation, the distribution of life's building blocks, and our cosmic heritage. What other ancient messengers await discovery in the depths of space? Share your thoughts below, hit that like button, and subscribe to Future Facts for more incredible cosmic discoveries. Until next time, keep looking up.